Okay, all right. Welcome everybody. As we agreed upon earlier on, tonight I'll talk about drawing crystals. And I've been thinking a little bit about how to do this best, because there's more than one program to draw crystals, of course. And so I decided, just like it is with learning how to walk, you do it step by step. So I suggest that we try to learn how to draw crystals by taking it easy and going step by step. So the program I would like to use is actually a program that can be used by everybody. Let's see. Okay, so I can share my screen, but first of all, I have to put the okay. All right, so let's start from, okay. So let's go back. And now if I share my screen, then I have to, okay, share. Okay, I hope everybody can see the web page on Smorf.
Yeah, we're good.
Okay, so Smorf is the drawing, the crystal drawing program that I would like to use tonight, and like to show you how it's working. And I noticed that Mark Holtkamp is among us. He is actually the man behind this program. He's the one who wrote it and who made the website and who also made all the drawings that you can see in both Mindat and Mineralien Atlas. Okay, so I'm actually very honored that he's here with us. Okay, so if you type in it's a very short name for the website. It's just smorf.nl. If you type that into your browser and hit enter, this is the page you're going to see, okay? Smorf crystal models. And then it says home, crystals, and drawing. Since we are going to talk about drawing, we click on drawing. And this is just a general page we see, okay? So we'll start with the most logical choice, and that is to have a look at crystals that have a lot of symmetry first. So if you look at crystals, or if you're looking for crystals that have a lot of symmetry, you find those crystals in the crystal system that is called the isometric crystal system, or sometimes also referred to as the cubic crystal system. Okay, so isometric, it's Greek, it stands for the same distances, the same measure. Iso is the same and metric is distance. Okay, so it actually says that a mineral that belongs to that crystal system, like for example fluorite, it will have the same distance on every crystal axis. Okay, so you have three crystal axes, the A, B, and C. And in the case of fluorite, the dimensions that are cut off by the crystal faces will be the same for every crystal axis. So one on A, one on B, and one on C. Also, the angles between the three crystal axes, so the angles between crystal axis A and crystal axis B is 90 degrees, between B and C is 90 degrees, and between C and A is also 90 degrees, okay? Let's have a quick look at, can you see the mindat.org page now?
Yes.
Okay, great. So we're quickly going to the isometric system. Okay, because, all right, here we have the crystallographic axis of the isometric system. And since they, on the three axes, they have the same length, the same distance, here they're actually using A1, A2, and A3 instead of using A, B, and C, but it's actually the same thing. And it's specified here, A is equal to B is equal to C. And here the angles alpha is equal to beta is equal to gamma is 90 degrees, okay? So that's actually what we saw here on the cell data too, okay? A is equal to B is equal to C is equal to 1, and the three angles are equal to 90 degrees, okay? Okay, so let's delete this one, okay? So, and let's delete this one too, okay? So now I don't have any crystals showing here on my left screen, okay? So what we're going to do is add a form. So we click on add form, and then we get HKL, which is the symbols for the three different for the distance of the axis that are cut off by a face. So let's keep it very simple and say that we're going to put 1 for A, and then 0 for B, and 0 for C, or which is actually the same, you know, so HKL in this case stands A being 1, B being 0, and C being 0. And we say a distance of 1, okay? So I put in here what is called the Miller indices of one phase, being the 1, 0, 0 phase. And if I click on draw crystal, it actually draws the crystal. So I do get a cube, okay? Now, why do I get a cube by just entering one set of Miller indices? That's because of the symmetry. As you know, isometric crystal system has 3 fourfold axes, okay? So both the A, the B, and the C axis are fourfold axes. So due to the symmetry, if you specify just one phase and you click on draw crystal, the program will use the symmetry defined by the mineral and will actually draw the whole crystal being the 1, 0, 0 form, okay? So what is typical of the isometric crystal system is that all the forms in which is a form is actually a set of crystal faces. So all the forms of the isometric crystal system are closed forms, okay? So in other words, by just specifying one set of Miller indices and by clicking on draw crystal, you will actually get a full crystal. Oops, sorry about that. Okay, so let's have a look at what we can do here. I'll rearrange my crystal here. Okay, so what can we do here? Well, we can, if we click on axis, you get to see the axis, okay? Oops, let's see, let's get a little bit higher. Yeah. Okay, if you click again on axis, axis disappear again, okay? Clicking on transparent will change the transparency. And if you click on opaque, you know, you will only see the faces that are directly facing you. Okay, if you click on Millers, it will actually show the Miller indices of the faces that you can see. So, and one downside of the Miller indices of this Smorf version, this online Smorf version, is that it doesn't show the, well, it shows the Miller indices of the form. It doesn't show the Miller indices of every face, because this is actually, if you add the axis and the Millers, it doesn't do both. Okay, so this face is the 100 face. This face is actually the 001 face. Okay, but all these faces of the 6 faces of the cube belong to the 100 form. Okay. Okay, what else? Oh yeah, something interesting too. If you click on, let's put the axis back on. If you click view on A, the program will actually slightly turn the crystal so the A axis is pointing towards you. Okay. If you click on B, it will actually do the same thing, but then B is pointing towards you. If you click on C, you will get the C axis that points towards you. Okay, clicking on Clinographic, it will show the most common way of showing a crystal, being the crystallographic projection. And if you click on rotate, it will actually make the crystal turn. And so you can see, you get a better feeling of what it looks like in 3D. Now, of course, this is just a cube, so it's not really something to get really excited about. Anyway, okay, let's try something different. We're still with fluorite isometric crystal system, so the most symmetry of any crystal system you have. Let's take another form. So instead of the 100 form, which was the cube, let's try, for example, or let's see what we get if we take the 111 form. So the 111 form, actually, you can translate it by saying a 111 face will actually cut off the same distance on the A axis, on the B axis, and on the C axis. Okay. So if you click on draw crystal, okay, that's funny. Well, let me. I probably didn't put the distance. There you go. Okay. So now you get both the indices. Let me take those off. Okay. The axis. Here you go. So what we get is an octahedron. Okay. So the octahedron has faces that cut off the A axis, the B axis, and the C axis at the same distance. Isometric. 111. Okay. So what happens if we take, for example, another form and we say that the face has to cut off 1 unit on the A axis, 1 unit on the B axis, and it has to stay parallel to the C axis. In this case, the 110 face is a face that cuts off 1 unit on A, 1 unit on B, but it stays parallel to the C axis. Okay. Oops. Let's draw the crystal and see what we get. Okay. So what we have now is a rhombin dodecahedron. So it's a dodecahedron stands for 12 faces, and all 12 faces are rhombs, so they call it the rhombin dodecahedron. This is the classic shape of a garnet, of the garnet family crystals. Okay. Maybe one more, or maybe not. No. Let's do something different. Let's delete this one and let's go back to our beginning. And so we're going to draw the cube again. Okay. Oops, sorry. There you go. So here we have a cube. Now, what is going to happen if we add another form? So we have the cube here. Now let's add the octahedron, okay? So we put in 1, 1, 1, and the distance from the center 1. So by saying that the distance is 1 from the center, both for the cubic form and for the octahedral form, we actually get we should get a combination of both forms that have the same dimension, more or less. And this is what we get. So we do get here the cubic faces, and here we got the octahedral faces. If we click on Miller's, you will see these are the cubic faces. That one too, that one too. And these are the octahedral faces, okay? The 1, 1, 1 face. And so by playing a little bit with these distances, you can make one form more important than the other. And more important than the other also means that the faces of that form get larger, or on the other hand, get smaller. So by raising the distance here, you actually make the form smaller. So let's see, instead of 1, if we put 1.5 for the cube and we say draw crystal, you see, the cube faces now have, well, they're much smaller. The octahedral faces are much larger. Okay, and what is kind of neat with this program is that you can actually do it in real time. So you can actually see what happens, which is kind of neat. And this might actually show you what will happen eventually if you start. Let's go back to, okay. So you start out with an octahedron, so to speak, and then okay, the octahedral faces, they grow more rapidly than the cubic faces, and then eventually they will grow so fast that they will disappear, and you will end with a cube. So this is kind of nice to see how two forms can interact. And of course, you can make it more complicated if you add a third form. Like, for example, in the case of, if we add a rhombin dodecahedron to the drawing, this is what we get. Some people might recognize certain fluorite crystals from Inner Mongolia. They frequently have this kind of shape. So you see here the cube faces that are slightly larger due to the distance that's slightly shorter. And then you have here the 110 faces, which are the rhomben dodecahedral faces, and then here the octahedral faces. Okay. All right, let's get back to the basics. And this is what we had in the beginning. So we added one form, being the 100 form. And for fluorite, because it was part of the isometric crystal system and had the most symmetry of all crystal systems, that one form was a closed form. It just the 100 form. In total, it has 6 faces. So four for around the C-axis, and then one on top and one at the bottom. A total of 6 faces for the cube, and all those 6 faces, they belong to the form 100. Okay. Now let's see what happens if we take another crystal, another mineral that does not have that elevated symmetry like fluorite does. So let's take a mineral, apophyllite, for example, that is not isometric, but it's tetragonal. Okay. So we'll delete any form and we'll start with adding our 100 faces. Okay. So that means, well, if we look at the cell data, so you have here the distance on A is 1, the distance on B is 1, the distance on C is 1.763. So there's a difference between, well, A and B are equal, but C is not equal to A and B. C is different from A and B. And the angles are still the same, okay, 90 degrees. So we add this form, the 100 form, and we click on draw crystal and nothing is happening. Why is that? Why isn't there anything showing? Well, it's because right now we only have one form, and in total the form is not closed. It's what is called an open form, and the program is unable to show that to us. Okay, so we have to add another form in order to close the crystal, so to speak, and to make it appear on the screen. So the faces that are missing are the 001 faces and 00-1 face. Okay, together they are the 001 form. So if we draw the crystal now, there you have that. Well, it looks like a cube, but it's not really a cube. It's a block. Yeah, you could call it a block, rectangular block. Okay. So it actually looks like a cube, but it's not. From a crystallographic point of view, it's not. Okay. So it's important to realize that when you're drawing crystals, that you the symmetry that the mineral that you're drawing crystals of, that the symmetry it or the crystal system it belongs to will be crucial for knowing how many forms you need to get a closed crystal, a closed crystal drawing. So if we go from the tetragonal crystal system, if we go to the orthorhombic crystal system, for example, by choosing barite, oops, okay, barite here. Okay, we delete any form. So here you see that now A is no longer equal to B, is no longer equal to C, but the angles are still rectangles. I mean, they're still 90 degrees. So the three axes, the three crystallographic axes are still perpendicular to each other, but the distance, the unit distance from on the three crystallographic axis is different. Okay. So if we add a form now, and we add the 1, 0, 0 form, and we click on draw crystal, it doesn't show anything, which is logic because our form is still wide open. Actually, by specifying this form, since we are dealing with the orthorhombic crystal system, this form actually only has two faces, the 1, 0, 0 face and the minus 1, 0, 0 face. Okay, if we add another, for example, the 0, 1, 0, and we click on draw crystal, it's still not showing anything because, again, our form is still not closed. So for the orthorhombic crystal system, we actually have to add a third form that will finally close our crystal. And here you got it. Now we have, again, what looks like a cube, but it's an orthorhombic block, so it has different dimensions in the three directions. So every direction, the A direction, the distance from the center to the face is different than the distance from the center to the B face, and is different from the center to the C face. Okay, these three different distances, but the axes are still at 90 degrees. They're still perpendicular. Okay. So for the orthorhombic crystal system, if we want to draw a block, we actually need three forms: the 1, 0, 0 form, the 0, 1, 0 form, and the 0, 0, 1 form. That's the absolute minimum that we need to draw a block. Okay. Okay, and then we can go even further. Well, let me delete these first again. Okay, and now we're going to Titanite. And Titanite, as you will see here, the orientation of the crystallographic axis has changed. So the B axis is still perpendicular to the C axis, but the A axis is no longer perpendicular to the C axis. There's an angle between A and C of 119 degrees, which you can see here. Okay. B is still perpendicular to A and perpendicular to C, but A is no longer perpendicular to C, but it is at an angle. So if we add the three basic forms here, being the 1, 0, 0, distance 1, draw crystal, of course, it's not doing anything because our crystal shape is still open. The drawing is still open. So again, 0, 1, 1, distance 1, draw crystal. Okay, yes, my mistake. Okay, if we draw the crystal now, it doesn't show anything because again, the crystal is not closed yet. So we still have to add a third form, being the 0, 0, 1. And now if we click on draw crystal, we will get our block, but it will no longer be a rectangular block, but it will be a block with an incline. Okay. So if we click on rotate, it will actually show you that the faces that cut off the A-axis are at an incline in respect to the C-axis. Okay. Okay. And we can go further down the drain, so to speak. Titanite is monoclinic. It still has a little bit of symmetry. It has a twofold axis that is perpendicular to a symmetry plane, which is what is written here. 2 stands for the twofold axis, and /M stands for perpendicular to a symmetry plane. So there's still a little bit of symmetry. If you go to the triclinic crystal system, then there's almost no symmetry at all. And for some crystals, you end up, if you want to have something that looks like a block, you end up by adding 6 forms, because every face, in worst case scenario, if you don't have any symmetry at all, you will need 6 to define 6 faces to get your block. Okay, so I'm not going to do that. We just wanted to show you something else. Okay, so as you've probably seen already, if you click here on the select mineral, you have a whole list of minerals that you can choose from and that are predefined in the database, the little database that's behind this program. Yeah, of course, you also have the hexagonal system and the trigonal system, but they're more or less similar to orthorhombic, and I mean, it's the same principle, so I'm not going into detail on those. But what I wanted to say, okay, for example, pseudobruchite, okay. So if you click on pseudobruchite, you will see that the cell data automatically get changed. So by seeing these 3 axes at 90 degrees, you know immediately that, and seeing that there's 3 different values here for A, B, and C, you know immediately that this is the orthorhombic crystal system. So pseudobruchite belongs to the orthorhombic crystal system. It has the symmetry MMM, which means it has 3 symmetry planes, and that's all. Okay, what I wanted to show now is if we go on, imagine that you want to draw a crystal of a mineral that is not part of the list. So how do you do that? Okay, well, it's not that complicated. First of all, what you can do is click on this. So it will, and then you delete everything here, okay? And so you don't fill in anything here because, well, you can always check to see if the mineral is in the list, but if it's not in the list, you just leave it like this. You go to MinDat. Let's see, for example, here, we can use, well, let's say that, let's take Adamite. I know it's in the list, but just for an example. Okay, so we have the mineral Adamite, okay, and we go down until we get to beyond physical and optical data, chemical. Okay, here you got the crystallography of Adamite. Okay, so Adamite is orthorhombic, and it has MMM, so which is the highest symmetry in the orthorhombic crystal system. Okay, here you get the cell parameters. You have a value for A, a value for B, and a value for C. Okay, so it's these values that you actually have to use in Smorf to get the same dimensions that are predefined for the other minerals here. So if you look at Adamite here, let's see if I can do a copy paste. I hope so. Yep, it works. So I take the 3 values here and put them in Smorf. Okay, and the 90 degrees are the, since it's orthorhombic, that is correct. So the 3, there aren't any angles specified here because orthorhombic by definition has 3 crystallographic axes that are perpendicular to each other. And here you got a note on the morphology, which is very interesting. So it says here, crystals of variable morphology, often elongated on 0, 1, 0, also elongated on 0, 0, 1. Rarely elongated on 1, 0, 0. Well, you only have 3 possibilities, right? Tabular at times with this crystal form or equant. Okay, so this stands for elongated along or parallel to the B axis. Okay, 0 means parallel. The first 0 means parallel to A. The 1 means it cuts off the B axis, and the 0, the third 0, well, the third digit being 0 means it's parallel to the C axis as well. So elongated along 0, 1, 0 means that it's elongated along the B axis, and you can actually see that right below here, that crystal drawing that's also made by Mark, made by Smorf. If we click on the axis, you will see the B axis. That's the axis of elongation. Okay, so this crystal actually nicely illustrates what we have just read here, often elongated on 0, 1, 0. Okay. All right, it says tabular at times 1, 0, 1 or equant. So let's try and see. We click on add form and we click on 1, 0, 1, distance 1. Click on draw crystal. And this is what we get for Adamite. Okay, let's orient it. This actually shows well, it looks like an isometric rhombus dodecahedron. So okay, let's add another face. Since it's normally elongated on the along B axis, we should have we should add the faces that are parallel to, let's see, parallel to the B axis. So, for example, the 0, 0, 1 face. Take a distance of 1. There you get. Okay, well, okay, I messed up. Okay, yeah, I see what's wrong. I'm still in the cubic point group. That's, of course, is not correct. I have to change it to MMM. Sorry about that. So that form doesn't do anything at all. So let's add the 0, 1, 0 face. Distance 1. There you go. Okay. So we have a closed crystal drawing here with two forms. We have the 101 form, which is there. And then we have the 010 form, which are the two faces here that cut off the B axis. And since we just read that crystals are often elongated along B, what we can do here is play with the distance so that the crystal will become more elongated. Okay, so if we add the distance to, if we increase the distance of the B faces from the center of the crystal, of course the crystal will become more elongated. So this is how you draw more elongated crystals. Okay. Now, okay, you could say this doesn't really look like an Adamite crystal. Normally an Adamite crystal has chisel-shaped terminations. So, and this is flat. So we need another form that will show those chisel shapes. So in order to get that, we need, instead of the 010, we need another form that will actually, make or show that chisel shape. And so that form is a face that will cut off the B axis, will cut off the A axis, but will be parallel to the C axis. So it has to be something like it cuts off the A axis, it cuts off the B axis, but it's parallel to the C axis, okay? So it has to be something like this. If we draw the crystal, there you go. And now if we add another face that actually is parallel to B and C and only cuts the A, then we can get a nice elongated crystal, or we could already, if we increase, see where we're going. Okay, this really looks more like an adamite crystal. Let me rotate it for you. Okay. And what is nice too is that with the mouse, you can actually turn it in any direction you want. So that if you are making a crystal drawing that, you know, you want the orientation of the crystal to be exactly the same as the crystal, the real crystal you're drawing, you can actually do it by manipulating the drawing here with your mouse. And if you want to have the standard orientation again, you just click on Crystallographic and there you get it. So standard orientation of crystal drawings, it's called the Crystallographic orientation, and it's it has the C-axis going well, it's parallel to your computer screen, and then the B axis also parallel to your computer screen, perpendicular to the C, and then the A axis is actually it's pointing more or less towards you, but at an angle, so it's not really facing you directly. It's at an angle that it comes out of the computer screen. And again, if you can click on these to show what the crystal looks like. If you look parallel along the A axis, or parallel along the B axis, or parallel along the C axis. Okay. There's also the possibility to color your different forms. So for example, here now, if we have the Crystallographic, that's an easy way also to distinguish between the different crystal forms. If you give them a different color. And you can eventually save your work by clicking on download, so that you download the file or the image. Normally what I do, whenever I'm ready with the crystal drawing, and when I'm happy with what I made, is this Crystallographic? Yeah, so let's make it transparent. What I normally do is I just use the snipping tool and do a copy and paste and put it wherever I want it. That's easy. Okay. All right, so something that we have to remember is that we have to adjust the point group. It's apparently not put to to 0, or it actually retains the point group of the previous mineral that you worked with. So that was a mistake that I made. I'm sorry about that. Just for fun, let's we still have a few minutes, so let's get another one. Let's see, what mineral are we supposed to well, what was the photo of the day? What was the photo of the day? Let's see what we have here. Yeah, Susanite. Okay, Susanite. Okay. So, well, let's take the middle one. It looks like a hexagonal. Well, it is trigonal. Okay. So trigonal. And here you have the cell parameters and the space group P3. Okay, let's see if we can find that in first of all, let's see if Susanite is in there. Nope, it's not. Well, that's a good that's a good thing. So, okay. Trigonal. Okay, these are the choices I have. And for Susanite, it's pyramidal. Okay. Pyramidal. Well, it has to be one of those. Let's see if I can find more information, because this isn't really helping us. Let's see if we find more in the Handbook of Mineralogy. Point group 3, so it's just 3. Point group 3, so which is the lowest symmetry of the trigonal system. 3. Okay, so we delete these. Okay, and now we're going to draw the crystal. Let's see what they say about common crystal faces. Now it says thin hexagonal plates. So hexagonal in this case being 6-sided. Let's have a look again at the Handbook of Mineralogy to see if they say something about. Here it says, oh, and it actually says the crystal system is hexagonal. Well, yeah, okay, yeah, hexagonal. There's a conflict, so to speak, between two. Well, there's two groups of people. Some people say there's only the hexagonal crystal system, and some people say no, there's an hexagonal crystal system and there's also a trigonal crystal system. Okay, it depends on the mineralogist you're talking to. Okay, so it says as equal to acute rhombohedral crystals modified by a prism and a basal pinacoid. Let's see if we can produce that. So we add a form. Let's see, we'll just add 1, 0, 0 at a distance of 1. We add another form. They wanted the pinacoid, so we need something to on top and on the bottom. So it would be a 0, 0, 1 phase, also a distance of 1. See if we already have. No, it only shows the pinacoid. Okay, so we have to add another form. Let's see what else they were saying. A prism. Okay. Small. So 1, 1, 0. Okay. And let's add another form, the 0. Well, we already have the 0, 0, 1. Okay.
I think you need to add the cell parameters.
Yeah, I was just going to say that.
Yes, you're correct. Yeah, thanks. Stupid me. Okay, cell parameters, absolutely. So here we have 907. And we have C. and C equals 1157. Okay. Okay, let's see what happens now. 1990, 120. 1990, 120. Trigonal. Okay. I'm stuck, I guess. I don't, but let's see the alpha beta. This is wrong too. Of course, this should be 60, 60, and then I actually don't know because there's 4 crystallographic axes, and I don't know what Smorf uses in this case. We could have gone to let's see. Well, let's see what they have for calcite. Okay, so they have it at 90, 90, 122. Okay. So what if we take this here? So there's yeah, since there's not much symmetry, I think what I need to have is a 0, 0, -1 phase as well. There you go. Yeah. Okay. That was my mistake. Since it only has the mineral Susanite only has a 3-fold axis. That's the only symmetry it has, and so I had defined an upper phase, which was the 0, 0, 1 phase, but I didn't define a lower phase, being the 0, 0, -1 phase. And as long as I didn't put that phase as another form to add to the crystal drawing, the crystal wasn't closed, so to speak, and so the program couldn't show the crystal. But now it can, because now it is a closed drawing. It has all the forms it needs, and so now we do have our Susanite crystal drawing. And with the phases that we have defined, this is what more or less what it looks like. Looks like, let's see, if we put it on Clinographic and we click on mirrors, it has the 110 and the 0, 100. Yeah, okay.
Herwig,
all right.
Herwig,
yes.
Is your cell data not right now?
My cell data is wrong again, yes, but that should, okay, let me change the cell data again. And let's see here, Susanite. Okay, so this should be, okay, doesn't change much. Which kind of makes sense that it doesn't change much, because we had similar data. I mean, it was 1.1 and then 1.3 or something like that. So it's doesn't really influence or change the crystal drawing. Okay, well, I think that's about all I can put in the first talk here on Smorf. There's other crystal drawing programs. Another one that I use on a fairly regular basis is Crystal Shaper. And the strength of Crystal Shaper is that you can actually modify the the shape of every single crystal face, whereas here the only thing that you can modify is the shape of the form. So if you increase the distance or lower the distance, it will do so for all the faces that belong to the same form. Whereas with Crystal Shaper, you can actually do it for just one face, which gives you more freedom to draw a crystal that looks more like a real crystal. Because real crystals normally, sometimes, you know, if you have like a real fluorite cube, it might be that some faces are slightly smaller than others. And so with Crystal Drawer, you can, Crystal Shaper, sorry, you can actually adjust every crystal face if you want to. All right, that's it. Any questions? Yeah, I think everybody's fallen asleep.
Absolutely not.
Not asleep.
Bamboozled.
Well, it's something that you have to play with a while to get used to it, but it's very handy, especially if you know, for example, you have a description of what the faces are of a mineral, but you don't have a drawing. So, you know, with this program, you can actually quickly, you know, make that crystal drawing and see what it looks like in 3D.
Yeah.
Herwig, I have a question, Herwig. Can you just select the mineral Susanite and put it in the box?
No, because it's not in this list. And so if it's not in this list, you can only put these in the box, and then it will show the data. But since Susanite is not in this list, I cannot select it. And so the only way to do the only way to work around it is what I showed you. You know, you take this, which is, well, you select no mineral, and then you have to adjust the point group here. For Susanite, it was 3, and then we had to adjust the cell data as well. So we modified the cell data for A, B, and C, and then we filled in the forms and we got our drawing. So that's the best we can do with this program for a mineral that's not in the list. Okay, there is, however, there's something else that let's see. If we go back to Smorf to the first page, you can see here that there's way more crystal drawings, and so here is select the mineral, and it might be possible that Susanite is here in this list. No, it isn't.
Okay.
Sometimes there's sometimes more minerals listed here than there is in the drawing section. But Mark hasn't made drawings of every mineral species, and so certain minerals will not be in the list. And then the only way you can do it is what I showed you. You know, just adjust all the parameters here, and then add the forms you want to add, and draw the crystal and see what you come up with.
Thanks, Herwig. I thought this was very good because I knew that Smorf existed, and I've kind of looked at it before and not really known what to do with those boxes, but I think I have a good handle on it now. So
Well,
very helpful.
Well, okay. Well, that's the goal. If you have if you have the feeling that you kind of know what to do with it now, that's the goal, then I am very happy.
One thing that was nice, I got multiple monitors, so I followed along with you. I put Mindat and Smorf up on one of the other monitors and followed along with what you were doing.
I think it's also good that you explained a little bit about the Miller indices as well, Herwig. And crystallography is not something that a lot of people know
Right.
a lot about. Don Pecks' articles are very good on that in Mindat.
Yes, I agree. Yeah, so I actually showed these, well, and I showed the one on the isometric crystal system, but all the crystal systems have an article on them, and they're extremely well done. I agree. Yeah. Yeah. And if you don't know where to find them, it's actually very easy. If you don't know where to find them, one thing to do is you go to the top of the Mindat page where you have a search thing and you put isometric, for example, and you hit enter. Okay. And then here you see article crystallography isometric system. So, you click on that one and then you get to, of course, that article on the isometric system. And then at the bottom of the article is where you find the links to the others. Okay. So here are the links of the other crystal systems. So it's always easy to find. You just have to put in one crystal system in that top box where you do a search, and then you get a link to one of the pages, and then you have all of them. Very easy. Of course, there's also the other, the more official path to wisdom, so to speak. If you click on learn, you have Mindat articles. You click on Mindat articles, and then you have all the articles. And okay, Donald Pecks articles used to be featured. Apparently, they no longer are. But you click here on title and you put in monoclinic, for example. Hit enter, and there you got it. Okay, crystallography monoclinic system. Click on monoclinic, and there you go. And again, at the bottom, where the references are, just above is the links to the others. So very easy to find them. And definitely worth reading all of them. And don't be afraid if you don't understand everything that's in there. It actually takes a couple of iterations. You have to read it and then, let it sit for a while and then read it again. And at the same time, try drawing, for example, a crystal of diopside. Click on diopside and click on the mineral name. So you get to see the crystallography of it here. So here you have all the information. It's monoclinic. This is so it has a twofold axis perpendicular to a mirror, symmetry plane. And these are the cell parameters. So the three values that you have to put in for A, B, and C. And then here you have that angle, the angle between the A axis and the C axis, which is 105. So this information, you have to put that into Smorf, unless, of course, diopside is in the list, and I guess it is because it's a very common mineral. Okay, so, here all the work has been done. So you might see that there's a difference in the cell data. You have 1091 and 059, whereas here with diopside, it has different numbers, and that's because here you have the real dimensions of the cell, and here you have the ratio. Okay, so you can also use the ratio, which is what is done here. 1091 0.59. That's exactly the same as what we see here 109, 1059. Okay. And then the B, 106.3, and here 105. Yeah, so it's almost identical. It depends also on the data source that you're using. Okay.
That's very good. Thank you, Herwig.
Well, you're welcome.
All right. Any other questions for Herwig? If not, then we will close this session, and remember to go and register for the next one so you can add it to your calendar if you haven't already done so. And we'll see you all back in 4 weeks' time.
Okay.
All right.
Very
All right.
good.
Thank you.
Thank you, Steve. Hopefully in Tasmania.
Hopefully, yeah. See you.
Herwig, it's time for some Hershey chocolates.
We're still not allowed to go into the US. We are still. I heard
We'll have
that
virtual chocolate.
Yeah. Well, I could show some here, but that I think that would be mean. Yeah. No, I heard something like mid-August that eventually the US would open its borders for Canadians, but I'm not sure about that. So we're just waiting and hoping that they will open their borders for Europeans as well, because for now, apparently, it's not apparently, for now, unless you have a family or a business trip, you're not allowed into the country. So
I think right now we can go to Canada, but it's questionable whether we could come back.
Yeah.
Yeah,
Okay.
there is that.
Yeah. So we'll just have to see. No, I hope at least by the time Tucson comes around that everything's kind of more or less back to normal. But you never know with the virus. I mean, it's it's hanging on. That's for sure.
Yeah.
And one of these days we'll get a variety that they got to tweak the vaccine for.
Yeah. Mm-hmm. Yeah. Well, we'll just have to see how it goes.
All right. Well, I'm going to end the session. So thank you.
All
everybody.
right. Okay. Thank you, Steve.
Talk
Bye.
again soon.
Okay,
Right.
thanks,
Control.
Herwig.